So I hope everybody had a good weekend and a good Valentine's Day. We're continuing with chapter 3, so make sure that you're finishing your chapter 3 reading by the end of this week. We will also have a homework that is due on Friday, so it'll due by 11:35 a.m. at the beginning of class on Friday. It will be a chapter 3 homework, and you will need to have it on engineering paper or paper that I've approved, and it is due at the beginning of class. So are there any questions about anything before I jump into doing notes? BV is already here snoring. So if you hear snoring in the background, I woke him up because I said his name. It's him. So hopefully there's nobody else sleeping that you can hear. All right, so I'm gonna get started. I'll make sure to have the chat pulled up as always, so please engage in the chat if you have any questions. And let's get my whiteboard all set up here. So I will be posting these notes, and the recording for, golly, I just want to move this thing. And the recording for today's class after class today. But all right, so I'm gonna get started. We were talking about last week, and we were applying it on Friday, this aspect of quality represented by the letter X. I almost call it quabity because there's an episode of The Office where there's like, they're asking Creed Bratton like what he does, and he's like, I don't know, like quabity assurance, because he can't remember quality assurance. And so I always say quabity. So if you hear me say quabity, it's because of The Office. All right, so quality has this term X where it's representing the amount of gas or vapor over the amount total. So we use this sub G marker to represent vapor or gas, and we use sub F to represent fluid or liquid. And so quality is only ever occurring with saturated liquid vapors. So it is only ever that table A4, A5. It's only ever in places where we're near saturation temperature. It is only ever in systems where you have some vapor, some liquid. That is the definition of quality. So if you see a question asking about quality, you automatically know what table to use. You are using your saturated liquid vapor table. We also have this equation for quality. We also have an equation for quality where we have some generic variable y is equal to y sub f plus quality times y sub fg. So if you remember, this could be enthalpy. Enthalpy of the system is equal to enthalpy of the fluid plus quality times enthalpy of the fluid vapor region. So that region between where a vapor and a fluid, you're all vapor, you're all fluid, that line. So if you remember this graph that we made here where we have compressed liquid, then saturated vapor, saturated liquid vapor, then saturated vapor, then superheated vapor, this whole line here is represented by this sub Fg. So this could be for enthalpy, it could be for internal energy, it could be for specific volume. So we could also use it for internal energy, we could use it for specific volume. We can use this equation in a lot of different kind of variables, which is why I do it with this generic formula of y. But if we look at rearranging this formula to isolate x, here's where on the worksheet on Friday, I was able to explain it to a few people, but I wanted to make sure I didn't leave anybody behind. If we were to rearrange this, we would get enthalpy is equal to, quality is equal to enthalpy minus enthalpy of the fluid over enthalpy of the liquid vapor, Fg. All right, so just rearranging this equation. Here's where we can get other equations for enthalpy. On Friday, we used the one where quality is equal to specific volume minus specific volume of the fluid over specific volume of the fluid vapor region. So this is the easiest way of getting quality, but there you can also rearrange this generic quality formula to isolate if you don't know anything about mass. If you remember what I was just saying, where the sub FG is representing that entire flat line of the saturated vapor region, that's why this is also going to be equal to enthalpy of the gas minus enthalpy of the fluid. So that whole region, right? So on that graph here, we have the vapor gas here, we have our fluid here. So if you're subtracting your vapor from your fluid, you're going to kind of get this whole line that's occurring here. All right, so that was one of the things that came up on Friday that I realized I hadn't necessarily explained well enough for my liking, so I wanted to go back over it. Are there any questions about the worksheet on Friday or quality or any of these equations? You okay? All right. So I want to review a little bit of saturated liquid vapor regions, superheated vapors, and compressed liquids. So the first one I'm going to go over is saturated liquid vapors. So this is this region, saturated liquid vapor region. We're at our saturation pressure and temperature typically. And this is represented by our so this is our area under the saturation curve. Saturation curve. Under the saturation curve, which should make sense if you've been doing your readings, but we have these curves where the critical point's at the top, and that saturation curve, everything under it is characterized by this saturated liquid vapor region. Typically, there's an element of quality. And we often use this, often used as a point of comparison, often used as point of comparison. So I'll show you some examples of this, but typically if we want to know if something is a superheated vapor or not, we don't start at superheated vapor and compare there. We start at saturated liquid vapor and see if it's if we're above saturation or below, anything like that. So we often use this as a point of comparison. So I start at table A4, A5, and if I am able to use those tables, if I can prove that this is where I belong, then that's great. If not, then it gives me a comparative. Okay, well, I'm way above saturation temperature. I need to go to superheated vapor. So these are table A4, A5 for water. I believe it's A12, A13. Yeah. So it's A11 and A12 for refrigerant. So this is in the 900 pages in your book, all the way in the back. And table A4, A5 are saturated liquid vapor of water. Table A11, A12 are your saturated liquid vapor tables for R135. Was that a question or just a little noise? Anybody have a question? All right, so with saturated liquid vapors, typically here's where we start. Here's what we assume we have until we can prove otherwise. If you see terms like quality, you absolutely have a saturated liquid vapor. If you're at a relatively normal pressure and temperature, you probably have a saturated liquid vapor, but we always kind of use this as a point of comparison. Our second phase of matter would be a superheated vapor. And when compared to a saturated vapor, compared to saturated vapor, so when we're comparing it to just this saturated vapor here, we have a superheated vapor up in that higher graph point. So when we're comparing just to a saturated vapor, we're at a lower pressure. So pressure is lower than Psat at a given temperature. So this is lower pressure. We're at higher temperature, so temperature is higher than Tsat at a given pressure. Higher temp. These are kind of the two big ones. So if you're given a temperature and your system of water is at 250 degrees Celsius, determine the internal energy. Well, you don't know if you should use your saturated liquid vapor table or if you should use your saturated vapor table. Well, you have a given pressure, you have a given temperature. You will be comparing your pressure that's occurring to your saturation pressure in your saturated liquid vapor table. And if your pressure is much lower, at a lower pressure, then you can assume it's a superheated vapor. There's too many terms. And vice versa, if you're told this system's at 1 megapascal and 400 degrees Celsius, what's the internal energy? Well, you can go to 1 megapascal. You can see what the saturated temperature is. If your temperature is much higher than that saturated temperature, then you're a superheated vapor. You have a higher specific volume typically as well. So specific volume is higher than the specific volume for the saturated vapor, so the subscript B, at a given pressure or temperature. You have to know pressure or temperature to really be able to use the tables right off the bat. Those are the first two columns, which is why all of these are at some given pressure or temperature. So higher specific volume. We also have a higher internal energy than just a saturated vapor at given pressure or temperature. Higher internal energy. And we have a higher enthalpy than a saturated vapor at a given temperature and pressure. Which all of these make sense, right? If you have a vapor that's recently vaporized, it's kind of close to its liquid form, or you have a superheated vapor, you can imagine with that extra heat or that lower pressure, we have a higher heat content, we have more internal energy, we're trying to take up more space, and we have higher temperatures, lower pressures. So all of these kind of make sense logically, and you can see how they would fit with a superheated vapor compared to a saturated vapor. All right, so here's a quick example. Determine the internal energy, which is U, of water at 20 PSI, PSIA, PSI, it doesn't matter, at 400 degrees Fahrenheit. So try to do that for like a couple minutes, see what value you get, and then we can go over it. So for those of you who don't have, who have an international version of the textbook, you might not have the English units, the A4A and the A5E. I'm sorry, A4E and A5E. So why don't you do 20 kilopascal and 100 degrees Celsius. Mm. Sorry, do 10 kilopascal. So Christian, there should only be one answer. Okay, so all right, so we are asked to determine the internal energy of water. So we know we're using water at 20 psi and 400 degrees Fahrenheit. So I mentioned that we pretty much always use the saturated liquid vapor tables as our point of comparison. So at a given pressure of 20 psi, I'm going to go to my table A4E because this is English units. So A4E in the 8th edition of the textbook is on page 954. I can look here at 954, I have A4E, and then on 956, I have A5E. So at page, so A5E on page 956 or thereabouts, at pressure 250 psi, or I'm sorry, 20, not 250, at 20 psi, my saturated temperature, my Tsat value is 227.9 degrees Celsius. I'm sorry, degrees Fahrenheit. So we are much higher. My temperature is much higher than my saturation temperature at this pressure, which means that I am a superheated vapor. So then I need to go to table A6E, which is on page 958. And across the top, I have my different pressures. So at pressure of 20 psi, which is in the first box in the second row, I can see that my internal energy at 400 degrees Celsius so my internal energy at 400 degrees Celsius and 20 psi is 1,145.7 BTU per pound mass. Nope, I'm sorry, that's for 20 psi. It's 0.1. 1,145.1 BTU per pound mass. It's the same thing if you were to do table A4, A5. So if you do table A4, A5, okay, let's look at table A5 at 10 kilopascal. Our saturation temperature is 45.81 degrees. So 45.81. Yeah, so Elizabeth, go with what I'm written here. 400 degrees Fahrenheit, 20 PSI, 100 degrees Celsius, 10 kilopascal. It's Fahrenheit. What page on the 9th edition? I'm on the page, but I don't see it. She's talking about your subscript on your U. All right, well, I feel like. So in the 9th edition, Layla, I was starting on page, so A6E is on page 942. And table A6 for metric units is on page 894. So they have the same heading. The pages are just like a few pages off. All right, so if we have 10 kilopascal and 100 degrees Celsius, when we look up 10 kilopascal in our saturated liquid vapor table for water, we have our saturation temperature of 45.8 degrees Celsius. So our saturation temperature of 100 degrees Celsius, our saturation temperature of 45 is lower than our temperature of 100 degrees Celsius, which means we are once again in a superheated vapor. So then we go to table 5, we go from table A5 to A6, and we have our pressure across the top. So 10 kilopascal is 0.01 megapascal. We know we're at 100 degrees Celsius. So our internal energy here of 100 degrees Celsius is equal to 2,515.5 kilojoules per kilogram. Was anybody not able to find it?
Can you repeat what that bottom number you just wrote is?
Yeah, this pen doesn't like to write 5 very well. So it's 2,000. 2,515.5 kilojoules per kilogram.
So once you determined it was a superheated vapor, you went to table A4 and
No. Table A4 and A5 are only for saturated liquid vapors.
okay, so what did you, one more time, what did you do when you determined it was a superheated vapor?
So here's where you go to the superheated vapor tables, which are table A6.
Gotcha.
And across the top, they're labeled superheated water. So superheated water. And it looks like these go on for several pages. So at least like 4 or 5 pages in my book. Table A4 and A5 are just labeled saturated water. So, other questions? Okay. So the last one, we have saturated liquid vapor, table A4 and A5. We have superheated vapor, table A6. Those are for water. They have their mirrored counterparts for R134A, but those are for water. The third one we have is compressed liquid. For compressed liquid, a lot of times we approximate this as a saturated liquid. Approximate as saturated liquid. So this is where we're going to use the generic variable y and then the subscript f. So the fluid, just a saturated liquid. So if you remember in this chart here, we have our superheated vapor, we have our compressed liquid, we have our saturated liquid vapor. This is our saturated liquid. This is our saturated vapor. So a lot of times our compressed liquid is happening just at lower temperatures or higher pressures. Lower temperatures or higher pressures, but we don't often use a separate table for these. Those of you with a newer edition of the book, on table A7 on page, table A7 on page 912. And that's in the 8th edition. In the 9th edition, that's for 8th. In the 9th edition, it is on page 896. This is a table for compressed liquid water. So it does have its own table in some of the newer editions of the book. Some of the older ones, I don't believe have that, but it does have its own table. If I were to ask you to use it on a homework or an exam, you would just be able to use the saturated liquid. You could use the saturated liquid vapor table. All right. Typically, the pressure of a compressed liquid is greater than the saturation pressure at a given temperature. So this is at a higher pressure. Remember, superheated vapors were at a lower pressure. And our temperature here is going to be lower than our saturation temperature at a given pressure. So this is the exact opposite of the superheated vapor. So here we're at a higher pressure, lower temp compared to saturated liquid vapor, and superheated vapor, we're at a lower pressure, higher temperature. So as a quick example, determine the internal energy, U, of water at 80 degrees Celsius and 5 megapascal. So right off the bat, I know 5 megapascal is a relatively high pressure. And I know that 80 degrees Celsius is not a particularly high temperature. So it's probably either a saturated liquid vapor, or compressed liquid. It's not going to be a superheated vapor. So if we use table A7, which is the compressed liquid table, I know all of you don't have it, which is why I'm not going to make you do it right now. But the table A7, if we look at pressure of 5 megapascal and a temperature of 80 degrees Celsius, our internal energy, 5 megapascal, 20 degrees, 80 degrees Celsius, our internal energy is 333.82 kilojoules per kilogram. If you were to look at your saturated liquid vapor table, at 5 megapascal, here's where we're at 5,000 kilopascal. If you look at your saturated liquid vapor table, so table A5 at 5,000 kilopascal, our T sat is 263 degrees Celsius. So we are at a much lower temperature than a saturated liquid vapor, which is why we know it would be a compressed liquid. So using our compressed liquid table, we get 333 kilojoules per kilogram. If we were to use table A4 or A5, so if we were to use table A4 and then use our saturated liquid values, so we would like internal energy of our system is approximated as the internal energy of our saturated liquid at 80 degrees Celsius. So at this lower temperature, this would be approximated to be 334.97 kilojoules per kilogram. Using table A4 at 80 degrees Celsius, and then looking up just the saturated liquid values.
So like you can use either table A4 or the compressed liquid water table, or this is just for the if we are looking for the saturated liquid versus the compressed.
So for a compressed liquid, only a compressed liquid, you can use either the compressed liquid table or you can use your saturated liquid vapor table and only use your saturated liquid values, because as you can see, these are very similar values. So a lot of times we just approximate our compressed liquid to be a saturated liquid. So you can use either table. It's probably easiest to use the saturated liquid vapor table, but whatever's easier for you. If we look at the error that's happening, so the error is the observed minus the actual over the actual. So observed would be our 334. This is our approximation, 0.97 minus 333.82 is our actual from our actual table over actual 333.82 times 100. If you plug this in, the error is about 0.34%, something like that. So the error is so low that we say like it's acceptable to just approximate using your saturated liquid vapor table. All right, so in general, as a rule of thumb, if your temperature is low at any given pressure, let me say that up front so I don't make it more confusing. At a given pressure, if your temperature is lower than your saturation temperature at that pressure, you have a compressed liquid. If your temperature is equal or about equal to your saturation temperature, you have a saturated mixture or a saturated liquid vapor. And if your temperature is higher than your saturation temperature, then you have a superheated vapor. So here's another quick example. determine the enthalpy of a system at 500 kilopascal and 250 degrees Celsius. So I'll give you a couple minutes to do that.
Since it says system, do we use the refrigerant or the water tables?
Oh, you're right. Sorry. I should have said water. I pulled this from part of another question. So yeah, I let that off. I'm sorry.
So then how would we know to use refrigerant instead? Like what would be the tip? to
I would
know
tell
that?
you.
Okay.
Yeah, I would tell you always if it's water or refrigerant. Or it would say something like a refrigerator has a system coolant. Something very obvious. Okay, anybody want more time? All right, so we know our pressure is 500 kilopascal, which is 0.5 megapascal. We know our temperature is 250 degrees Celsius. So if we start looking at table A5, we have 500 kilopascal, so T sat at 500 kilopascal is equal to 151 degrees Celsius, 151.83 degrees Celsius. So our temperature is greater than our T sat at a given pressure. So we are a superheated vapor, which means that we need to move to table A6. So if we go to table A6 and we look at 0.5 megapascal, and one way to check that you're converting between megapascal and kilopascal is if you look at the top of the row here, it gives you your pressure equals 0.5 megapascal. And in parentheses, it says T sat is equal to 151.83 degrees Celsius. So now you know for sure, okay, yeah, that's the same one as my 500 kilopascal, I converted correctly. Because I know it gets kind of like, wait, is that 500 or is that 0.5 or is that 5 or is that 0.05? Like sometimes it gets a little fuzzy up there. Well, that's another way to check yourself. All right, so if we look at this little box on page or table A6, we look at the second temperature down, which is our 250 degrees Celsius, and we look over to enthalpy. Our enthalpy value here is 2000. 2,961.0. Am I lining that up correctly? It looks weird with my finger right now. Kilojoules per kilogram. All right, anybody confused about how I got that? So typically the superheated vapor ones are a little bit easier, because if you remember on Friday, in order to get enthalpy with a saturated liquid, a lot of times you have to use that equation of your saturated liquid vapor plus your quality times your liquid vapor region. You have to kind of solve around for it a little bit more because you do have this complex mixture. Superheated vapor, it's all vapor. So there's one value, you know, the table is smaller. So it's sometimes nicer. It's just hard to figure out where you're going at first. All right, so any questions?
So you're saying our enthalpy is just a value we found because it's a saturated, a superheated vapor?
Yep. Your enthalpy of your system for a superheated vapor is that enthalpy term. Well, that's your specific enthalpy. If you wanted full enthalpy of your system, you would need to multiply it by the mass of your system. All right. So I'm gonna work another problem now, unless there's any questions. All right. Hopefully this one works. I did this one late last night. So there might be mistakes. Just let me know if you see any. Okay, Leila, so we look at 0.5 PSI. So you're gonna look at 0.5 megapascal. PSI are in English units. So that might be in the other tables, the E tables, but for the table we just looked at, we were looking at 500 kilopascal. And 500 kilopascal, if you go from kilo to mega, it's 1,000 times higher. So you would need to divide by 1,000. So it's 500 kilopascal is 0.5 megapascal. And the superheated vapor tables are all in megapascal. All right. Okay, so here's an example. Determine the pressure of water determine the pressure of water vapor at 370 degrees Celsius and 0.004953 cubic meter per kilogram. So determine the pressure of water vapor at 370 degrees Celsius and 0.004953 cubic meter per kilogram. All right, so we want to determine this use A, steam tables, B, ideal gas equation of state, and C, the generalized compressibility chart. So right away, we know that we're going to be working with a water vapor because we're told this, and we're also told to use an ideal gas. So we're either working with a saturated vapor or a superheated vapor. Um, we don't know a set pressure for the system. That's what we're trying to figure out. So it's a little bit different than the example problems than we've been doing before. We have our temperature that's given. Sorry, I'm just checking something really fast. All right. So first we're gonna look up what sort of values that we need. So we're gonna look up first in table A1, we're gonna look up our R value, our critical temperature value, and our critical pressure value. So in table A1, we have our R value for water, which is 0.4615 kilojoules per kilogram Kelvin, or kilopascal meter cubed kilogram Kelvin. Our critical temperature for water is 647.1 Kelvin, and our critical pressure is 22.06 megapascal. These are all from table A1. We could also look up our critical specific volume, which is 0.0560 cubic meter per kilomole. But we haven't really done anything with that yet, but just know that you can get it from that table as well. And since we are given some specific volume information here, you know, you never know. We're not going to use it right now, but just know that you can get it from there. All right. So we're just told that this is water vapor. We're not told that it's a superheated vapor or anything. So we're going to go on the assumption that we're working with just a water vapor, a saturated vapor. So for part A, when we're going to use the steam tables, we're going to use table A4. And we're going to use table A4 at 370 degrees Celsius. So our P sat at 370 degrees Celsius from table A4 is 21,044 kilopascal. It's almost the very last line in that table, second to last. The last is 373.95. So it's almost the very last line in there. It's a very, very high saturation pressure. If you remember, a superheated vapor is typically at a lower pressure than the saturation pressure at a given temperature. So it could be a superheated vapor. We're not super really concerned with it right now because we know what the saturation pressure is. And we're only told water vapor. All right, and then for part B, we're going to use the ideal gas equation of state. So this is where P specific volume equals RT, or pressure equals RT over specific volume. And we know R, we know T, and we know specific volume. So we're able to just plug and chug here. Our R value is 0.4615 kilopascal cubic meter kilogram Kelvin. Our temperature is 370 degrees Celsius, but we need it in Kelvin. So we're going to add that to 73 to get it in terms of Kelvin. And our specific volume is 0.004953 cubic meter per kilogram. So we're going to have these kelvins cancel. We're going to have our cubic meter cancel. We're going to have our kilograms cancel. We're left with kilopascal. That's a pressure unit. That makes sense. That works. If we do this out, I get 59,912.1 kilopascal. Which is very unlikely and very different from the table, which is saying that this is not behaving as an ideal gas. It's not a good approximation for these types of problems. All right, so for part C, we're going to use the generalized compressibility chart. So for part C, we're using the generalized compressibility chart. So in order for us to use the generalized compressibility chart, so far we've used our temperature reduced and our pressure reduced, but we don't know our pressure. Pressure is what we're trying to find. So we're going to have to find some other variable on the generalized compressibility chart for us to use. And the one that we're given here is specific volume. So we're going to use temperature reduced and our pseudo reduced specific volume. Our temperature reduced is easy. It's just our temperature over our critical temperature. Our temperature here is 370 plus 273 to convert it to Kelvin, which is 643 degrees Kelvin. And our temperature critical is 647.1 Kelvin. So our temperature reduced is 0.994. Okay, so we have one part of what we need for the generalized compressibility chart. Now we need to get our pseudo reduced specific volume. The equation for this that I gave you last week and is also written on the generalized compressibility chart is our actual specific volume over our R value, and then the ratio of our critical temperature to our critical pressure. So we are given our actual specific volume in the problem statement. We looked up R in table 1, the A1, and then we looked up our critical point values for pressure and temperature. So we have everything we need to solve this. So 0.004953 cubic meter per kilogram divided by our R value, 0.4615 kilojoule kilogram Kelvin, our temperature critical, which is 647.1 Kelvin, divided by our pressure critical, which is going to come up to the top here of 22.06 megapascal. We also know that this unit can be, I should have written it the other way, I apologize, kilopascal cubic meter divided by kilogram Kelvin. And we know that 22 megapascal is going to be 22,060 kilopascal. I'm going to just convert that here to make it easier with the units. So now we're going to have our kilopascal cancel. We're going to have our cubic meter cancel. We're going to have our kilograms cancel, and we're going to have our Kelvin cancel. So we're going to get a unitless value, which is what we're looking for a pseudo-reduced specific volume. When we multiply this all out, we get a value, or at least I did, of 109.3 divided by 298 0.6, which gives us 0.37. So our temperature reduced is 0.994, and our pseudo-reduced specific volume is 0.37. So I'm gonna say our temperature reduced is about 1, and our volume reduced is about, I think I did 0.35. All right, so then if we go to our generalized compressibility chart, let's see if I can find one that's a little easier to see. All right, so if we go to our generalized compressibility chart, this is for lower pressures. The top one's for lower pressures, pressure reduced between 0, and 1. And then the lower one is for your higher pressures. We're gonna assume based on our first two answers that this is likely a higher pressure. But also when we look at the generalized compressibility chart and we look at our temperature reduced values and our pseudo reduced specific volume values, this is kind of closer to what values we want. If we look at this top one, our pseudo reduced specific volume values are all higher than we need. And that makes sense because our pressure is much lower. All right, so we're gonna go to the second table for higher pressures, average pressures. And here we have our temperature reduced value of 0.994, which we're gonna approximate to be 1. So we have this lowest temperature reduced value here, 1, this curvy line down here. And then we have our specific pseudo reduced specific volume of 0.366, which we're gonna approximate to be 0.35. So we wanna know where this line and this line connect. So we're gonna follow our pseudo reduced specific volume line of 0.35. We're gonna see where it hits our temperature reduced volume, our temperature reduced value of 1. So it appears to be hitting about here. We're gonna follow that down to the pseudo reduced volume at the bottom, and it looks like we're at about 1. So then we know that our
What was the value for PR in this situation?
that's what we're trying to find. So
Ah.
I just found it to be 1.
Got it.
So okay. Do you want me to go over how to do that again?
No, sorry, I got it now.
Okay.
I realize
just took it down.
it's a variable.
All right, so based on our generalized compressibility chart from our pseudo reduced specific volume and our temperature reduced, we were able to use that generalized compressibility chart and find that our reduced pressure value is going to be about 1. So we want to determine the pressure unit using the generalized compressibility chart. We've determined the pseudo reduced pressure. So how do we get pressure back from pseudo reduced pressure or reduced pressure? Well, if you remember, our reduced pressure equation is just our pressure over our pressure critical. So then our pressure is just going to be our pressure reduced times our pressure critical. So our pressure reduced times our pressure, times our pressure critical is going to be our pressure reduced we just found to be 1. Our pressure critical we found to be 22.06 megapascal. So our pressure is going to be approximately 22 megapascal. Our steam table gave us a value of about 21,000 as our saturation pressure. 21,000 kilopascal, which is about 21 megapascal. Our ideal gas gave us 59 megapascal. And our generalized compressibility chart gave us 22 megapascal. So as you can see, an ideal gas equation is not good for these types of high pressure situations where it's not behaving ideally. This is not a good way of solving this problem. And particularly since you're not told if it's a superheated vapor and you're not exactly sure if you should use which Dean table, the generalized compressibility chart is a really nice way of finding your answer. Okay. Yeah, go ahead.
Sorry, what was that part again? Like, how can you tell if it's superheated vapor or super saturated vapor?
So that's what I was going over at the beginning of class with all of the, you know, like you compare it to your saturation pressure, you compare it to your saturation temperature. So at a given temperature, if your pressure is lower than your saturated pressure, then you are a superheated vapor. But here we aren't given a pressure, so we have nothing really to compare it to. We could, so that's why I was trying to have you practice at the beginning of class. For this problem, it's a little tougher because you're not given any sort of pressure. If you were to go, one way that you can do it is if you were to go to table A4 and you looked at the line for 300 degrees, 370 degrees Celsius, your specific volume of your saturated vapor is going to be 0.004953, which indicates that you are just going to be a saturated vapor, because this is the same specific volume that you were given. But if you remember, if your specific volume is higher than your specific volume of your saturated vapor at a given temperature or pressure, so if you have a higher specific volume, then that would be a superheated vapor. So if this value had been 0.006, it would have been an indication that we're a superheated vapor.
Oh, okay, thank you.
You're welcome. Yeah, other questions? Okay, I want to go over one more example and then we will call it a day. So this is example 3-3, where a mass of 200 grams of saturated liquid water is completely vaporized. Is completely vaporized at a constant pressure. At a constant pressure of 100 kilopascal. Determine the volume change and the energy transfer. A mass of 200 grams of saturated liquid water is completely vaporized at a constant pressure of 100 kilopascal. Determine the change in volume and the energy transfer. All right, so first things first, we are told that we are going from a saturated liquid to a saturated vapor. So we are going from this saturated liquid to a saturated vapor. We are covering this plateau line. So saturated liquid water is completely vaporized. So our saturated liquid is completely turned into our saturated vapor. So we are covering this liquid vapor line. Our pressure is constant, which is an isobaric system. And we know that we have some sort of change in volume. So maybe it's like a piston type system, and that energy is being added to the system to vaporize the water. Probably something like heat, right? We're heating up this water to vaporize it, and it's expanding in the volume. So if you put a closed piston cylinder of water on your stove and heated it up, all of that water would eventually boil, become vapor, and expand because the vapor is going to take up more space, have more pressure. All right, so we know that we're going to be working with table A4 and A5 because we're a saturated liquid vapor. And we're going to be interested in volume change. So for the first part, Emerson, for the first part, we're going to look at a volume change. So I'm going to look at table A5 to look at my specific volume values. I'm looking at table A5 because my pressure is constant. My temperature is what's changing. My pressure is constant. So at 100 kilopascal, my specific volume of my vapor is 1.6941 cubic meter per kilogram. And my specific volume of my liquid is 0.001043 cubic meter per kilogram. And we know that my specific volume of my liquid vapor region is equal to the specific volume of my vapor minus the specific volume of my liquid, which is equal to 1.6941 minus 0.001043 cubic meter per kilogram, which is going to equal pretty much 1.6941, but 1.6931 cubic meter per kilogram is our specific volume for a liquid vapor region. So we know that this system was completely changed from a saturated liquid to a saturated water. So this volume change that's occurring here, this specific volume that's associated with this liquid vapor, is going to be the same as the change that we're interested in. So our volume change is going to be the mass of this liquid vapor times the specific volume of our liquid vapor. We know the mass of our liquid vapor system is 200 grams. The mass is held constant for the whole saturated mixture. And we know that our specific volume for our liquid vapor change, our liquid vapor region, is 1.6931 cubic meter per kilogram. I'm going to convert 200 grams to kilograms to have the same units, and then 1.6931 cubic meter per kilogram. So my change in specific volume is going to be 0.3386 cubic meters. Next, I'm going to look at my energy transfer. Based on reading the problem, I am not likely to be transferring kinetic energy, potential energy, internal energy. I'm going to be transferring heat content. So my energy transfer here is really asking for my enthalpy. My enthalpy is an energy term. It's associated with heat content, changing heat content. So my enthalpy of my liquid vapor is going to be the amount of energy needed to vaporize a substance. Amount of energy needed to vaporize a substance. Make sure you're reading the chapter because there is a lot of new nomenclature. So vaporization, latent heat, all of these things are in the chapter. So my enthalpy of my liquid vapor is going to be equal to the mass of my liquid vapor, which is constant, times my specific enthalpy of my liquid vapor. So I know my mass is given to me, and I need to look up my energy of my liquid vapor. So I can look this up once again from table A5 at my constant pressure of 100 kilopascal. So on that same line, looking at 100 kilopascal, I go over to my liquid vapor enthalpy term. It's nice because for specific volume, there's only vapor and liquid. There's no liquid vapor like the sub Fg, but for enthalpy internal energy, they do have this value of this difference that's occurring here. So I can just look up the fact that I have 2,257.5 kilojoules per kilogram of enthalpy in this phase change between water and vapor. So 2,257.5 kilojoules per kilogram. I just looked up this value from the table. And then together, these would be 451.5 kilojoule. I'm going to say this is positive energy that's being transferred to the water from the heating unit. So it's being heated by an external force in the surroundings. Okay. So any questions about the table, what I've been going over, anything that we've been doing so far? All right, well, please start working on the homework. You should be able to do all of it. I'm going to do some more problem solving and examples on Wednesday. I have one problem that's pretty long that we'll do. And I will see you all on Wednesday if there's no questions.
Have a good day.
All right, have a good day, everyone. Bye, thank you. Yeah, Kat, that sounds good. Just email it to me. I don't take attendance, but just in case.